There's a place in the universe where cold isn't just a sensation, it's a state of existence so extreme, it defies everything we know. Picture this: atoms slowing to a near standstill, heat vanishing into nothingness, and temperatures plunging to within a hair's breadth of absolute zero, the coldest possible temperature in existence. These aren't scenes from a sci-fi movie. They're real, mind-bending corners of the cosmos where the rules of physics twist into something almost unrecognizable. And what happens in these frozen realms doesn't just stay there. It reshapes our understanding of reality itself. Think about the coldest you've ever felt. Maybe it was a winter morning when the air bit at your skin, or a gust of wind that seemed to freeze your bones. Now multiply that cold by millions, and you're still only scratching the surface of the chill we're talking about. Out in the vast expanse of space, there are places where temperatures drop to just a fraction above absolute zero, where molecules move so sluggishly they might as well be trapped in cosmic molasses. These aren't just curiosities, they're laboratories of the universe, revealing secrets about how matter behaves under conditions so extreme they challenge the very foundations of science. What if I told you that studying these icy abysses could unlock answers to some of the biggest questions we have? From the swirling depths of distant nebulae to the carefully controlled environments of cutting-edge labs on Earth, these frigid frontiers hold clues about the birth of stars, the nature of dark matter, and even the origins of life. It's a journey into the unknown, where every discovery feels like peeling back another layer of the universe's deepest mysteries. So bundle up, because we're about to venture into the coldest places in existence, and what we find there might just change everything. Cold in space isn't just about shivering astronauts or frosty surfaces, it's a fundamental shift in how the universe operates. Imagine a world where heat isn't just scarce, but nearly non-existent, where the very concept of warmth feels like a distant memory. That's the reality in the deepest voids between galaxies, where temperatures hover just a whisper above absolute zero. But what makes this kind of cold so different from the winter chill we experience on Earth? The answer lies in the dance of atoms themselves. Here's the thing: temperature is really just a measure of how fast particles are jiggling around. The more energy they have, the hotter a substance gets. But when you strip away that energy, slowing atoms to a crawl, you approach the ultimate limit, absolute zero. At this point, particles stop moving entirely, frozen in place by the laws of physics. Yet, even in the emptiest corners of space, true absolute zero remains out of reach. Why? Because the universe itself won't allow complete stillness. Tiny quantum fluctuations, like ripples in an otherwise motionless pond, keep particles ever so slightly active. These extreme conditions aren't just scientific curiosities, they're cosmic laboratories. In places like the Boomerang Nebula, one of the coldest known natural regions in the universe, temperatures plummet to just 1 degree above absolute zero. That's colder than the background glow of the Big Bang itself. Here, molecules move so sluggishly that they behave in ways that defy our everyday experience. Gases don't just cool, they collapse into bizarre states of matter, revealing quantum effects normally hidden at warmer temperatures. And it's not just about distant space. Scientists recreate these conditions in labs on Earth, using lasers and magnetic fields to chill atoms to within a billionth of a degree of absolute zero. In these ultra-cold environments, matter starts acting like waves, particles sync up in perfect unison, and new states of existence emerge, like Bose-Einstein Condensates, where thousands of atoms merge into a single quantum entity. These experiments don't just push the limits of physics, they help us understand everything from superconductors to the very fabric of space-time. So when we talk about the coldest places in the universe, we're not just measuring degrees, we're peering into a hidden realm where the rules rewrite themselves, and every discovery cracks open another door to the unknown. The Boomerang Nebula isn't just another pretty cloud in space, it's a record-breaking cosmic deep freeze, holding the title of the coldest natural place we've ever discovered. Floating 5,000 light-years away in the constellation Centaurus, this ghostly structure isn't shaped by chance. Its distinctive bow-tie appearance comes from a dying star at its core, furiously ejecting gas at speeds over 160,000 kilometers per hour. That's fast enough to race from Earth to the Moon in less than 2 seconds. But here's the twist: as this gas expands outward at breakneck speed, it cools so dramatically that temperatures inside the nebula plummet to just 1 degree above absolute zero. That's colder than the void of space itself, colder than the afterglow of the Big Bang, so cold that even the faintest whisper of heat feels like an intrusion. What makes the Boomerang Nebula so special isn't just its temperature, it's how it got there. Most dying stars puff away their outer layers gently, like a slow exhale. But this one is practically coughing its insides into space, creating a rapid expansion effect similar to how aerosol cans chill when you spray them. The physics behind this is mesmerizing. As the gas expands, it does work against the surrounding vacuum, and that energy loss translates into a drastic temperature drop. The result, a nebula so frigid that even light seems to move sluggishly through its icy tendrils, and the implications go far beyond setting cosmic records. By studying the Boomerang Nebula, astronomers get a front-row seat to the final act of a star's life. The way it sheds its outer layers offers clues about how our own sun might behave billions of years from now. But there's more. This extreme environment acts like a natural laboratory for chemistry that would be impossible to replicate on Earth. Molecules here don't just slow down, they start behaving in bizarre ways. Normally unstable compounds can form and persist, giving scientists a rare glimpse into how complex chemistry works in the most hostile corners of the universe. Some researchers even speculate that these frigid zones could be cradles for the building blocks of life, where sluggish reactions allow delicate organic molecules to assemble without being torn apart by heat. Yet the Boomerang Nebula isn't just a relic of stellar death, it's a preview of the future. Over the next few thousand years, its expanding gases will continue cooling, eventually dissipating into the interstellar medium. By then, we might have even colder discoveries waiting for us, but for now, this cosmic icebox stands as a reminder of how extreme and surprising the universe can be, pushing the boundaries of what we thought possible and rewriting the rules of physics one frozen molecule at a time. While the Boomerang Nebula holds the cosmic record for natural cold, scientists on Earth have achieved something even more astonishing. They've built machines that out-chill the universe itself. In labs from Massachusetts to Geneva, researchers use lasers and magnetic fields to manipulate atoms with such precision that temperatures drop to within a billionth of a degree above absolute zero. That's colder than any known natural environment in existence, a testament to human ingenuity pushing the boundaries of what even space can do. Here's how it works. Imagine trying to slow down a speeding train by firing ping-pong balls at it. That's essentially what scientists do with atoms. They blast them with carefully tuned laser beams, each photon acting like a tiny nudge to sap the atom's energy. As the atoms lose momentum, their movement slows to a crawl and temperature plummets. But lasers alone aren't enough. To trap these ultra-cold atoms in place, researchers use powerful magnetic fields, creating a kind of invisible refrigerator where particles hover in near-perfect stillness. The result, a speck of matter so cold that quantum effects, usually drowned out by thermal noise, take center stage, and that's where things get truly bizarre. At these temperatures, atoms stop behaving like discrete particles and start acting like waves, overlapping and merging in ways that defy classical physics. They form exotic states of matter, like Bose-Einstein Condensates, where thousands of atoms synchronize into a single quantum entity, moving in perfect unison. It's as if an entire crowd suddenly started dancing in flawless harmony, every individual stepping in perfect time. These condensates aren't just laboratory curiosities, they're windows into phenomena like superconductivity, where electricity flows without resistance, or superfluidity, where liquids defy gravity and climb walls. The implications are staggering. Imagine computers that harness quantum weirdness to solve problems in seconds that would take conventional machines millennia. Or power grids that transmit electricity with zero energy loss, revolutionizing how we store and distribute energy. These ultra-cold experiments are already paving the way for technologies that sound like science fiction, from quantum sensors capable of detecting minuscule gravitational waves to atomic clocks so precise they could measure the subtle distortions of spacetime itself. Yet the real magic lies in how these earthbound experiments complement cosmic discoveries. By recreating the extreme conditions of space in the lab, scientists can test theories about the quantum underpinnings of the universe, from dark matter's elusive properties to the strange behavior of particles at the edge of black holes. It's a two-way street. Nature's coldest places inspire human innovation, and human innovation helps decode nature's deepest mysteries. So while the Boomerang Nebula might hold the title for natural cold, it's in these lab-grown deep freezes that we're rewriting the rules of reality itself. When atoms get cold enough, the universe starts playing by a whole new set of rules so strange they make the weirdest sci-fi look tame. Picture a liquid that defies gravity, creeping up the sides of its container and escaping like a ghost. Or particles separated by light years that somehow mirror each other's movements instantly, as if connected by invisible threads. This isn't fantasy, it's what happens when matter approaches the coldest temperatures possible, revealing a hidden quantum realm where our everyday intuition falls apart. Take superfluids, for example. Cool helium down to near absolute zero, and suddenly it loses all friction, flowing endlessly without slowing down. Drop some in a beaker, and it'll climb the walls and spill over the edge, not because it's being poured, but because it's literally defying gravity. This happens because at these extreme temperatures, quantum effects dominate. The atoms begin to sync up, moving as a single wave rather than individual particles. It's like an entire crowd suddenly marching in perfect lockstep, their movements so coordinated that obstacles like viscosity simply vanish. But the real head-scratcher is quantum entanglement. Imagine two electrons spinning in opposite directions, separated by a vast distance, say, one on Earth and another on Mars. Measure one, and the other instantly flips to match, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it seems to break the universe's speed limit, the speed of light. Yet in the ultra-cold environments of labs and deep space, this phenomenon isn't just theoretical. It's measurable, repeatable, and foundational to cutting-edge tech like quantum computing. Why does cold reveal these quantum quirks so clearly? Heat is chaos at higher temperatures. Particles jitter and collide, drowning out subtle quantum effects. But when you strip away that thermal noise, the underlying quantum reality emerges, like a signal finally clear of static. This is why scientists use ultra-cold setups to test theories about black holes, dark matter, and even the nature of time itself. The colder the experiment, the sharper the window into these deeper layers of physics becomes, and the implications stretch far beyond the lab. Quantum entanglement could revolutionize communication, enabling unhackable networks where information is teleported, not transmitted. Superfluids might lead to frictionless machinery or new ways to harness energy. Each discovery in this icy quantum frontier doesn't just add to our knowledge, it rewrites what we thought was possible, proving that the coldest places in existence are also the most revealing. Deep in the coldest reaches of space, an invisible cosmic detective story is unfolding, one that could rewrite everything we know about the universe's hidden architecture. Dark matter, that elusive substance outweighing visible matter 5 to 1, leaves its fingerprints everywhere, in the way galaxies spin too fast to hold themselves together, in the way light bends around empty patches of space. Yet despite decades of searching, we've never directly caught a glimpse of it. That might be because we've been looking in the wrong environments. Some of the most promising clues aren't in blazing stars or violent collisions, but in the quiet, frozen voids where temperatures flirt with absolute zero. Here's why cold matters. Dark matter particles, if they exist, interact so weakly with normal matter that their signals are drowned out by the slightest thermal noise. It's like trying to hear a whisper in a thunderstorm, but in the frigid expanse between galaxies or within ultra-cold lab experiments, that noise fades away. Hypothetical particles like actions ghostly, lightweight candidates for dark matter could finally make their presence known under these icy conditions. They arise to shift and ripple in response to magnetic fields. Actions might convert into detectable photons only when the surrounding environment is cold enough to eliminate interference. It's as if the universe's best-kept secret only reveals itself in a hushed, frozen library. The hunt is already underway. Experiments like ADMX, a high-tech action detector chilled to near absolute zero, scan the cosmic silence for these faint signals. Meanwhile, astronomers train telescopes on cold molecular clouds in space, where the absence of heat might allow dark matter interactions to leave subtle imprints. Even the afterglow of the Big Bang, cooled over billions of years to just a few degrees above absolute zero, could carry distortions caused by dark matter's gravitational whispers. These aren't just shots in the dark, they're deliberate strategies to corner an invisible opponent by exploiting the one condition where it might slip up: extreme cold. What's at stake goes far beyond ticking a box in the standard model of physics. If dark matter particles are found in these frozen frontiers, they could explain why galaxies formed the way they did, why the universe's expansion is accelerating, and even whether there are hidden dimensions lurking beneath reality's surface. The coldest places in existence aren't just barren wastelands, they're treasure maps, pointing to the missing pieces of a puzzle we've only begun to assemble. And with every experiment that pushes temperatures lower, we get closer to turning the universe's deepest secret into its greatest revelation. The cosmic microwave background isn't just leftover heat, it's the universe's oldest baby picture, a snapshot frozen in time when everything was just 380,000 years old. Stretching across the entire sky at a bone-chilling 2.7 Kelvin, this faint glow is colder than liquid helium, colder than Pluto's shadowed craters, yet it carries the warmth of creation itself. Imagine holding a thermal imprint of the cosmos when it was a seething plasma of particles and light, before stars or galaxies even existed. That's the CMB, a relic so pristine, its subtle temperature variations, tiny fluctuations no stronger than 100,000th of a degree, hold the blueprint for everything we see today. How does something so cold tell such a fiery story? In the early universe, particles and light were locked in a frenzied dance, too energetic to combine. But as expansion stretched space, everything cooled. Protons and electrons finally slowed enough to form atoms, releasing light that's been traveling ever since. Red shifted over billions of years into microwaves. What makes the CMB extraordinary isn't just its age, it's the imperfections. Those minuscule temperature differences reveal where matter clumped slightly denser, gravitational seeds that would one day grow into galaxies and superclusters. It's like finding the faint pencil sketches beneath a masterpiece, showing how the universe went from smooth soup to structured cosmos. Scientists decode this icy whisper using instruments like the Planck satellite, which mapped the CMB with such precision it could detect variations smaller than a snowflake's shadow on a football field. These maps confirm mind-bending truths. That ordinary matter makes up less than 5% of the universe, with dark matter and dark energy dominating the rest. The CMB even carries scars from the universe's explosive infancy, evidence of gravitational waves that rippled through space-time during cosmic inflation, a period when the universe expanded faster than light itself. But here's what's truly astonishing: the CMB is cooling. As the universe keeps stretching, those microwaves will redshift further, their energy fading. Billions of years from now, future civilizations might need telescopes far more sensitive to detect this echo at all. For now, though, it remains our clearest window into the universe's origins, proving that even the deepest cold isn't empty, it's alive with history. Every photon is a messenger from a time before time, and decoding their story reshapes not just our past, but our future. Neutron stars are cosmic contradictions born in the unimaginable heat of a supernova, yet cooling over millennia into some of the coldest objects in the universe. Picture the aftermath of a star's violent death, collapsing into a sphere so dense that a teaspoon of its material would weigh 1 billion tons on Earth. At their surfaces, temperatures can drop below 1 million Kelvin, a number that sounds scorching until you realize it's thousands of times cooler than their explosive origins. For stellar remnants, that's practically an ice age. What makes these ultra-dense objects so fascinating isn't just their temperature, it's what happens inside them. Packed into a space no wider than a city, the core of a neutron star crushes matter so tightly that protons and electrons merge, forming a sea of neutrons. But under that unfathomable pressure, even neutrons might break apart, dissolving into something even stranger: quark-gluon plasma, a primordial soup of particles that hasn't existed freely since the first microseconds after the Big Bang. It's as if the star's core becomes a time machine, recreating conditions not seen for over 13 billion years, and here's where cold meets extreme. While the surface chills, the core's insane density traps heat, creating a bizarre gradient where matter exists simultaneously under conditions of extreme pressure and relative cold. This duality makes neutron stars natural laboratories for physics we can't replicate on Earth. For example, their crust's crystalline layers, just meters thick, are so strong that starquakes can release energy equivalent to a magnitude 32 earthquake. Meanwhile, their interiors might host rivers of superfluid neutrons, flowing without friction like the helium in a lab, but on a cosmic scale. The implications stretch far beyond curiosity. By studying how neutron stars cool, scientists test theories about how matter behaves at densities so high, even atoms collapse. Some models suggest their cores might contain strange matter, a hypothetical form so stable it could convert anything it touches. Others propose their factories for heavy elements like gold and platinum, forged in their crushing gravitational fields. Every flicker of X-rays from their surfaces, every pulse of radiation from their magnetic poles carries data about this alien physics. Yet the coldest neutron stars hold another surprise. They're timekeepers. Isolated from the heat of companions, some spin with such perfect regularity that their pulses rival atomic clocks. These cosmic metronomes, called pulsars, allow astronomers to test Einstein's theories with precision, measuring how their gravity bends space-time or how their spins gradually slow as they radiate energy away. So while neutron stars might seem like relics of destruction, they're anything but dead. They're dynamic, extreme, and eerily cold proof that even in the deepest freeze, the universe never stops revealing its secrets. Drifting through the blackness between stars, vast clouds of gas and dust linger in a state of suspended animation. Chilled to temperatures so low, they make the vacuum of space seem warm by comparison. At just 10 to 20 Kelvin, these interstellar clouds are cosmic freezers, where atoms move sluggishly enough to bond into molecules that would never survive the chaos of warmer environments. Water, formaldehyde, even simple sugars, these icy grains are sprinkled throughout the darkness like ingredients waiting for a recipe. But these aren't just random chemical experiments. They're the birthplaces of stars, the raw material of solar systems, and possibly the delivery system for life's building blocks across the galaxy. Picture one of these clouds up close. A single cubic centimeter might contain just a few thousand molecules so sparse. It's a better vacuum than anything we've created on Earth. Yet over millions of years, gravity works its magic, pulling these scattered particles together until pockets grow dense enough to ignite nuclear fusion. That's how stars are born, from the coldest, darkest places in the cosmos. But the real wonder isn't just the stars, it's what happens in the leftover materials swirling around them. As a newborn star flickers to life, its heat pushes lighter elements outward, leaving behind a disk of dust and ice where planets will eventually form. And trapped within those frozen grains are the same complex molecules that drifted in the original cloud. This is where the story gets fascinating. In the frigid depths of these clouds, chemistry takes on a whole new dimension. Normally, molecules break apart when they collide, but at these temperatures, they stick together like snowflakes in a blizzard. Water ice coats dust grains, forming microscopic skating rinks where atoms can slide and rearrange. Ultraviolet light from distant stars, though weak, provides just enough energy to trigger reactions without destroying the delicate structures. The result: molecules like methanol, hydrogen cyanide, and even amino acids, the precursors to proteins, can form and survive. Astronomers have found over 200 different compounds in these clouds, some as complex as ethyl formate, the molecule that gives raspberries their scent. It's a reminder that the universe isn't just a sterile void, it's a chemist's workshop, quietly assembling the pieces of life in the coldest corners of existence. And when a star system forms, these molecules hitch a ride on comets and asteroids, seeding new worlds with the ingredients for oceans, atmospheres, and perhaps even biology. But here's the twist: these clouds aren't permanent. Over time, radiation from nearby stars or shockwaves from supernova can heat them up, dispersing their contents back into the interstellar medium. It's a cycle as old as the galaxy itself. Cold clouds collapse, stars ignite, and when those stars die, they scatter enriched material back into space, ready to form new clouds, new stars, and maybe, just maybe, new possibilities for life. So while these freezing nurseries might seem like silent waystations in the cosmos, they're anything but passive. They're dynamic, evolving, and ultimately, the reason we're here to ponder them at all. Far beyond the last whispers of Pluto's orbit, where sunlight is 1,000 times weaker than on Earth, lies a frozen graveyard of our solar system's infancy, the Oort Cloud. Picture a vast, spherical shell of icy debris stretching nearly a light year into space, so distant that even our fastest spacecraft would take tens of thousands of years to reach it. Here, temperatures hover around 5 Kelvin, just 5 degrees above absolute zero, so cold that molecules freeze in place like statues, preserving ancient chemistry unchanged for billions of years. These aren't just frozen rocks, they're cosmic time capsules holding raw materials from the swirling disk of gas and dust that birthed our planets. What makes the Oort Cloud extraordinary isn't just its cold, it's how perfectly it preserves the past. Unlike asteroids or inner solar system comets, these icy bodies have never been warmed by the sun's rays or altered by collisions. Each one is a snapshot of the early solar system, a recipe book of ingredients from before Earth existed. When gravitational nudges, perhaps from a passing star or the Milky Way's tides, send one tumbling inward, it transforms into the blazing spectacle we call a comet. As it nears the sun, its frozen gases vaporize, trailing that iconic glowing tail. But hidden within that spectacle are priceless clues, water molecules with isotopic fingerprints matching Earth's oceans, and complex organic compounds like formaldehyde or hydrogen, cyanide, the same molecules that may have seeded life on our planet. The implications are staggering. Some scientists argue that long-period comets, those originating in the Oort Cloud, could have been cosmic delivery trucks, ferrying water and probiotic chemistry to early Earth during the chaotic bombardment of our planet's youth. It's a poetic twist. The coldest place in our solar system might hold the keys to how life's building blocks arrived in a warm, wet cradle. Even more tantalizing is the possibility that these icy wanderers carry materials from even farther away. The Oort Cloud likely captured objects from interstellar space during the sun's journey through the galaxy, meaning some comets could be samples of other star systems' alien chemistry preserved in deep freeze. Yet studying this distant frontier isn't easy. The Oort Cloud's objects are too faint and far for direct observation with current telescopes. Instead, astronomers rely on the rare comets that visit the inner solar system, analyzing their compositions to piece together the cloud's secrets. Missions like the European Space Agency's Comet Interceptor, set to launch in 2029, aim to visit one of these pristine icy bodies, potentially unlocking answers about our origins. For now, the Oort Cloud remains a shadowy realm, a reminder that the coldest corners of our cosmic neighborhood aren't just barren wastelands, they're libraries of frozen history waiting for their stories to thaw. Black holes might seem like the ultimate cosmic infernos, devouring everything in their path with temperatures soaring into billions of degrees. Yet even in these maelstroms of destruction, patches of cold persist like frost forming on the rim of a volcano. These eerie cold spots, detected by instruments like the Event Horizon Telescope, aren't just quirks of physics. They're vital clues helping us decode the most mysterious objects in the universe. Take the supermassive black hole at the heart of Galaxy M87, the first ever directly imaged. Its glowing accretion disk, a whirlpool of superheated gas spiraling toward oblivion, should radiate blistering energy uniformly. But nestled within that fiery disk are darker, cooler regions where radiation dips dramatically. These aren't empty voids, they're shadows cast by the black hole's mind-bending gravity, warping spacetime so severely that light itself gets twisted away from our view. It's as if the black hole is sculpting its own silhouette out of the very heat it generates, leaving behind a fingerprint of cold in the chaos. Why does this matter? Because these shadows are more than just cosmic illusions. By analyzing their size and shape, astronomers can measure a black hole's spin, a property as fundamental as its mass. Faster spinning black holes drag spacetime around them like a whirlpool, distorting their shadows into asymmetrical crescents. Slower ones cast rounder, more uniform silhouettes. It's a celestial balancing act. The hotter and more violent the surroundings, the sharper the cold shadows become, revealing details no telescope could capture directly. But the real surprise is what these cold spots tell us about black holes' diets. Not all accretion disks are created equal. Some are turbulent and uneven, with clumps of cooler gas drifting like icebergs in a plasma sea. Others flicker unpredictably, their shadows shifting as magnetic fields snap and reconfigure. These variations hint at how black holes consume matter, whether in steady gulps or erratic bursts, and how they influence their host galaxies over billions of years. And here's the twist: even the coldest shadows are hot by human standards. The cool regions near M87's black holes still sizzle at millions of degrees. Yet compared to their surroundings, they're icy oases, proving that temperature is always relative. This delicate interplay of heat and cold challenges our assumptions about extremes, showing that nature rarely deals in absolutes. So the next time you picture a black hole, don't just imagine a pit of endless fire. Think of it as a dynamic arena where light and shadow dance, where gravity and radiation conspire to create patterns we're only beginning to understand. In the universe's most violent neighborhoods, even the coldest corners have stories to tell, and they're rewriting the rules of astrophysics one shadow at a time. Absolute zero sounds like the ultimate finish line for cold, a temperature where every atom stops dead in its tracks and heat vanishes completely. In theory, it's minus 273.15 degrees Celsius, the point where all thermal motion ceases. But here's the catch: the universe has a built-in rule that prevents anything from ever reaching that perfect stillness. Quantum mechanics insists that even in the deepest freeze, particles can't fully stop vibrating. They're always jittering thanks to something called zero-point energy, a fundamental hum of the cosmos that keeps the void from ever going completely silent. This isn't just a tiny loophole in physics, it's a revelation about how the universe works. Think of zero-point energy like the faintest whisper of static on an otherwise silent radio channel. No matter how much you adjust the dial, that background noise never fully disappears. In quantum terms, it means particles are perpetually dancing, even in the emptiest, coldest corners of space. This energy isn't heat, it's something more primal, woven into the fabric of reality itself. So why does the universe refuse absolute zero? It all ties back to Heisenberg's uncertainty principle, which states that you can never perfectly pin down both a particle's position and its momentum. If atoms truly stopped moving, we'd know exactly where they were and how fast they were going, a direct violation of quantum law. Instead, nature enforces a kind of restless minimum, ensuring particles always retain a faint buzz of activity. This has wild implications. For one, it means cold isn't just the absence of heat, it's a delicate balance between energy and entropy, where quantum effects take the wheel. In labs, scientists push temperatures to within a billionth of a degree above absolute zero, creating Bose-Einstein Condensates where atoms merge into a single quantum wave. Yet even there, zero-point energy lingers, a reminder that perfect stillness is an illusion. Out in space, this quantum restlessness shapes everything from the behavior of neutron stars to the way dark matter might interact with itself. It's why the Boomerang Nebula, colder than the afterglow of the Big Bang, can't quite hit absolute zero, and why the universe, no matter how cold, never truly sleeps. Superconductors might sound like science fiction, but they're one of the most tangible gifts extreme cold has given to modern technology. Picture a world where electricity flows without losing a single watt of energy, no heat, no resistance, just pure, unimpeded current. That's the magic of superconductivity, a phenomenon that occurs when certain materials are cooled to temperatures so low, their electrons stop colliding with atoms and pair up, gliding through the material like synchronized skaters on frictionless ice. The catch: most superconductors only work at temperatures colder than deep space. Traditional ones, like niobium tin alloys, demand cooling with liquid helium, which hovers just 4 degrees above absolute zero. That's why early applications were limited to niche uses, like the powerful magnets in MRI machines, where superconducting coils generate stable magnetic fields to peer inside the human body without the energy drain of conventional systems. But the real game changer came with the discovery of high-temperature superconductors, materials that achieve zero resistance at comparatively balmy temperatures. Think -135 degrees Celsius, cold enough to use liquid nitrogen instead of rare, expensive helium. This shift cracked open a world of possibilities. Take maglev trains, which float above their tracks on superconducting magnets, eliminating friction and hurtling passengers at speeds over 600 kilometers per hour with eerie silence. Or prototype power cables that could one day transmit electricity across continents with near-zero loss, slashing energy waste and revolutionizing grids. Even quantum computers rely on superconductors chilled to near absolute zero to maintain the fragile quantum states of their qubits. Yet the dream goes further. Scientists are now chasing room temperature superconductors, materials that could ditch cryogenics entirely and bring zero resistance power into everyday life. Imagine levitating cars, ultra-efficient wind turbines, or batteries that never degrade. Recent claims of breakthroughs, like the controversial LK99, have sparked both excitement and skepticism, highlighting just how transformative this technology could be. What makes superconductors so extraordinary isn't just their efficiency, it's how they force us to rethink the relationship between cold and innovation. By harnessing the bizarre physics of ultra-low temperatures, we're not just building better gadgets, we're rewriting the rules of energy itself. And as research pushes the boundaries of what's possible, one thing becomes clear: the coldest places in the universe aren't just curiosities, they're blueprints for the future. Imagine a substance so cold that thousands of atoms forget their individuals and start moving in perfect unison, like a school of fish turning as one, or a chorus singing in flawless harmony. That's the bizarre reality of Bose-Einstein Condensates, a fifth state of matter that defies everything we know about physics at everyday temperatures. When chilled to within a whisper of absolute zero, certain atoms like rubidium or sodium undergo a quantum identity crisis. Their wave-like natures stretch and overlap until they merge into a single, sprawling superatom, a ghostly quantum entity that can span millimeters yet behave as though it were a single particle. Creating this exotic state is no small feat. Scientists use lasers and magnetic traps to slow atoms to a crawl, sapping their thermal energy until they're barely moving at all. At these temperatures, quantum effects, usually drowned out by the chaos of heat, dominate the scene. The atoms enter a shared quantum state, losing their individuality entirely. It's as if an entire crowd suddenly started moving with the precision of a ballet dancer, every atom perfectly synchronized with its neighbors. The implications are staggering. In a Bose-Einstein condensate, light slows to a crawl, photons hitch rides on atoms to form bizarre hybrid particles called polaritons, and vortices spin without friction, mimicking the behavior of cosmic phenomena like neutron stars. Researchers have even used BCs to simulate black holes in the lab, studying how sound waves, yes, sound, behave like light trapped by gravity. These experiments aren't just academic curiosities, they're testbeds for theories about space-time, quantum gravity, and the nature of reality itself. But the real promise lies in technology. Because BECs are exquisitely sensitive to tiny changes in gravity or magnetic fields, they could revolutionize sensing. Picture earthquake detectors that feel tremors before they strike, or mineral surveys that pinpoint oil deposits with pinpoint accuracy. Quantum computers, too, could benefit. BECs might help stabilize qubits, the fragile building blocks of quantum calculations, by providing an ultra-cold, noise-free environment where quantum states last longer. Yet perhaps the most mind-bending aspect is what Bose-Einstein Condensates reveal about the universe's hidden layers. At temperatures this low, matter doesn't just behave differently. It reveals a side of reality normally invisible, where quantum weirdness isn't the exception but the rule. Every experiment with these ultra-cold superatoms peels back another layer of the cosmos's deepest mysteries, proving that sometimes to see the universe clearly, you have to cool it down to almost nothing. Antarctica may be the coldest place on Earth, but when stacked against the cosmos, its icy extremes start to look almost cozy. The continent's record low of -89.2 degrees Celsius is brutal enough to freeze breath in midair and turn rubber into brittle shards. Yet just beyond our atmosphere, the temperature drops to levels that make Antarctica seem tropical. The void between galaxies averages a mere 2.7 Kelvin colder than the afterglow of the Big Bang itself. That's the difference between a winter storm and a realm where heat barely exists at all. But here's the twist. Antarctica's McMurdo dry valleys come eerily close to mimicking the harshness of space. These frozen deserts, untouched by rain for millions of years, are so dry and cold that scientists use them as stand-ins for Mars. The valley's rocky terrain, blasted by katabatic winds roaring down from the polar plateau, mirrors the red planet's desolate landscapes so well that NASA tests rovers and life detection equipment here. It's a proving ground for the technology that might one day uncover microbes in Martian soil or the icy moons of Jupiter. What makes these comparisons invaluable isn't just about bragging rights for cold. Studying how life persists or doesn't in Antarctica's extremes helps us redefine the boundaries of habitability. In the dry valleys, microbes huddle inside porous rocks, surviving on fleeting traces of moisture and sunlight. If life can cling on here, it might lurk in similar niches on Mars or Europa. Meanwhile, the near-perfect vacuum of interstellar space, with its absence of heat and pressure, pushes those limits even further. Some organisms, like tardigrades, can survive the vacuum by entering suspended animation, hinting that life might endure even in the void between stars. The real lesson lies in the contrast. Antarctica teaches us how biology adapts to cold with shelter and time, while space reveals the absolute edge of physical possibility. Together, they sketch a roadmap for interstellar exploration, showing us where to look, what to protect against, and how to design missions that can withstand the universe's deepest freezes. Whether it's a rover drilling into Martian ice or a probe venturing into the Oort Cloud, these frigid frontiers aren't just obstacles, they're guides pointing the way to the next great discoveries. Exoplanets like Ogle 2005 BLG3 90LB redefine what it means to be frozen. With surface temperatures plunging to -220 degrees Celsius, this distant world makes Antarctica feel like a tropical getaway. But here's the astonishing part: beneath its icy shell, there could be an ocean. Not a frozen wasteland, but a liquid expanse, churned by tidal forces from its host star, creating pockets of warmth where life might cling to existence. It's a paradox that turns our search for habitable worlds upside down. The coldest surfaces might hide the most promising environments for life. Take Europa, a moon in our own solar system, as a preview. Beneath its cracked, icy crust lies a global ocean twice the volume of Earth's seas, kept liquid by Jupiter's relentless gravitational kneading. Now imagine that scenario playing out light years away, on exoplanets where the freezing void of space meets the simmering heat of tidal friction. These ice worlds don't just endure the cold, they weaponize it, using thick ice layers as insulating blankets that trap geothermal heat or energy from radioactive decay below. The result, subsurface lakes or even vast oceans, shielded from the lethal radiation and vacuum of space, where chemistry could brew the ingredients for life undisturbed. The implications are staggering. While we once focused on planets in the Goldilocks zone, where temperatures are just right for liquid water on the surface, ice worlds expand the playing field. A planet flung far from its star, or even a rogue world drifting between galaxies, might harbor subsurface oceans if it has the right mix of internal heat and insulating ice. Some models suggest these hidden seas could persist for billions of years, longer than Earth's oceans have existed. That's not just a niche habitat, it's a cosmic refuge, a place where life could survive long after its star has dimmed. But how would we detect something we can't even see? Astronomers get creative. They look for indirect clues like slight wobbles in a planet's orbit hinting at subsurface sloshing, or plumes of water vapor erupting through cracks in the ice similar to the geysers spotted on Saturn's moon Enceladus. Future telescopes might analyze the glow of reflected starlight off icy surfaces, searching for chemical signatures like methane or oxygen that could betray microbial activity below. The coldest exoplanets aren't just curiosities, they're test cases for resilience. If life can thrive in the dark, under crushing pressure and near freezing temperatures, it means the universe could be far more hospitable and far stranger than we ever imagined. Every frozen world we discover isn't just expanding the map of the cosmos, it's rewriting the definition of home. Brown dwarfs are cosmic misfits, too massive to be planets, yet too puny to ignite the nuclear fires that make stars shine. Picture an object dozens of times heavier than Jupiter, floating in space with just enough mass to briefly glow dull red before fading into a frigid twilight. The coldest of these failed stars barely push past room temperature, hovering around 27 degrees Celsius, warmer than your freezer but colder than a summer day. That might not sound extreme until you realize these objects should, by all rights, be blazing infernos. Their existence forces us to rethink the very definition of what makes a star. How does something so massive stay so cool? Unlike true stars, which fuse hydrogen in their cores, brown dwarfs lack the gravitational muscle to sustain that reaction. They might briefly burn deuterium or lithium, but these fuel sources sputter out fast, leaving the dwarf to slowly cool over billions of years like a dying ember. The result is a celestial object that defies categories too hot to be a gas giant, too cold to be a star, and full of atmospheric quirks that baffle astronomers. Some have clouds of molten iron or sand, while others boast storms so vast they'd swallow entire planets. Yet these cosmic oddballs aren't just curiosities, they're missing links in our understanding of stellar evolution. By studying brown dwarfs, astronomers can pinpoint the exact mass threshold where a gas giant becomes a star. That boundary, known as the hydrogen fusion limit, sits around 80 times Jupiter's mass. Anything below it becomes a brown dwarf, anything above ignites into a star, but nature loves blurring lines. Some brown dwarfs orbit stars like planets, while others drift alone through space like rogue stars. There's even evidence of free-floating brown dwarfs in interstellar space, untethered to any solar system, glowing faintly with residual heat from their formation. The coldest brown dwarfs, classified as white dwarfs, are the most enigmatic. Discovered only in the past decade, they're so chilly that their heat signatures blend into the cosmic background. Telescopes like the James Webb Space Telescope have to hunt them in infrared, peeling back layers of their atmospheres to spot methane, water vapor, and even signs of ammonia clouds. These discoveries aren't just about cataloging weird objects, they're rehearsals for finding life beyond Earth. The techniques used to study brown dwarfs' atmospheres are the same ones that'll analyze the air of distant exoplanets. So while brown dwarfs might seem like stellar failures, they're actually cosmic Rosetta Stones. They teach us that the universe doesn't fit neatly into boxes, that between the blazing stars and the frozen planets lies a spectrum of possibilities, each with its own secrets to share. And sometimes the coldest objects hold the hottest clues. Time moves differently when things get cold, not in the way you might think, but in ways that twist the fabric of reality itself. Einstein's theory of relativity taught us that gravity slows time. The stronger the pull, the more clocks drag their feet. But extreme cold plays its own subtle game with time, bending the rules through the strange behavior of atoms. At temperatures near absolute zero, particles slow to a crawl, vibrating so sluggishly that quantum effects take over. This isn't just about molecules moving slower, it's about time keeping itself becoming unnervingly precise. Atomic clocks, the most accurate timekeepers ever built, rely on this principle. Cool atoms like cesium or strontium to near zero temperatures, and their vibrations become so regular that these clocks would lose less than a second over the entire lifespan of the universe. That's 15 billion years of flawless ticking. The colder the atoms, the less thermal noise interferes with their oscillations, allowing scientists to measure time with mind-bending accuracy. It's as if cold doesn't just slow atoms down, it sharpens time's edges, revealing a clarity usually drowned out by the chaos of heat. But here's where relativity sneaks in. While cold itself doesn't warp time like gravity does, the precision of ultra-cold clocks lets us test Einstein's predictions in ways he never imagined. Take two clocks, one on Earth's surface, the other in space. Even a slight difference in gravity causes them to tick at different rates, a phenomenon called gravitational time dilation. Cold atomic clocks, with their razor-sharp accuracy, can detect these tiny discrepancies, proving that time isn't just a universal constant, but a flexible thread woven into the fabric of space-time. The real magic happens when cold meets extreme gravity. Near a black hole where time slows to a crawl under immense gravitational pull, the behavior of ultra-cold matter could reveal even stranger effects. Hypothetically, if you could place a Bose-Einstein condensate, a cloud of atoms chilled to near absolute zero near a black hole's event horizon, quantum mechanics and relativity would collide in ways we're only beginning to theorize. The condensate's wave-like atoms might stretch or distort, offering clues about how space-time itself behaves under such extreme conditions. So while cold doesn't directly bend time like gravity does, it gives us the tools to see time's true nature, not as a rigid ticker but as a fluid, malleable dimension. Every experiment with ultra-cold atoms peels back another layer of this mystery, showing that the coldest places in the universe aren't just laboratories for matter. They're windows into time itself. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Every second, trillions of these nearly massless phantoms zip through your body, born in the hearts of exploding stars, nuclear reactions, and even the Big Bang itself. Yet despite their staggering numbers, they barely leave a trace, interacting so weakly with matter that detecting them feels like trying to catch smoke with your bare hands. That's where the coldest places on Earth come in, transforming from icy wastelands into the perfect hunting grounds for these cosmic specters. Take the IceCube Neutrino Observatory, a colossal detector buried deep in the Antarctic ice. Here, temperatures plunge low enough to freeze out the thermal noise that would otherwise drown out neutrino signals. The setup is ingenious. Over 5,000 sensitive optical sensors are embedded in a cubic kilometer of pristine ice, waiting for the rare moment a neutrino collides with an atom. When that happens, the impact creates a fleeting burst of blue light called Cherenkov radiation, a faint shimmer in the darkness, like a single match struck in a cavern. Without the extreme cold keeping background interference at bay, that tiny flash would be lost forever. But why go to such lengths to catch particles that seem to do nothing? Because neutrinos are cosmic messengers carrying secrets from the most violent events in the universe. When a star goes supernova, 99% of its energy escapes as neutrinos, making them the first signal of stellar death. They're also time travelers of a sort. Some of the neutrinos hitting Earth today were born in the early universe, offering a snapshot of conditions we can't observe any other way. Even more intriguing are high-energy neutrinos, likely forged in the jets of supermassive black holes or colliding galaxies, which could help map the invisible web of cosmic rays crisscrossing space. The cold plays another critical role. It preserves the ice's clarity, ensuring light from neutrino collisions travels farther before scattering. It's like turning Antarctic ice into a giant lens, magnifying signals that would be imperceptible anywhere else. And the deeper the ice, the better pressure transforms the lower layers into an ultra-dense, bubble-free crystal, perfect for tracking neutrinos' paths with pinpoint accuracy. What makes these ghost particles so fascinating isn't just their stealth, it's what they reveal about extremes. Neutrinos born in supernova endure temperatures of trillions of degrees, yet by the time they reach us, they're as cold as the void they traverse. They're living contradictions, embodying both the universe's fiercest fires and its deepest freezes. And with every one we catch, we're not just solving a particle physics puzzle, we're reading a love letter from the cosmos, written in a language of ice and starlight. Quantum computing doesn't just push technological boundaries, it redefines the very meaning of cold. At the heart of these revolutionary machines are qubits, the quantum counterparts to classical bits, capable of existing in multiple states simultaneously thanks to the bizarre laws of quantum mechanics. But there's a catch: qubits are incredibly fragile. The slightest vibration or trace of heat can disrupt their delicate quantum states, causing errors that render calculations useless. That's why the world's most advanced quantum computers operate at temperatures colder than the vacuum of space, often within a few thousandths of a degree above absolute zero. To achieve this, engineers use elaborate cryogenic systems resembling high-tech freezers, with nested cooling stages that gradually strip away heat. Liquid helium chills the outer layers, while specialized dilution refrigerators tackle the final temperature plunge, isolating qubits in an environment where atoms barely twitch. It's like trying to balance a house of cards in the eye of a hurricane, except the hurricane is the warmth of your own breath, and the cards are atoms holding the keys to unprecedented computational power. The payoff for mastering these icy extremes could reshape civilization. Imagine designing new life-saving drugs by simulating molecular interactions atom by atom, a task far beyond today's supercomputers. Or cracking the code of high-temperature superconductivity, enabling lossless power grids that could slash global energy waste. Even artificial intelligence stands to leap forward, with quantum algorithms optimizing everything from traffic flows to climate models in seconds. Companies like IBM and Google aren't just racing to build bigger quantum processors, they're competing to create the coldest, most stable environments on Earth, where quantum coherence can last long enough to solve real-world problems. Yet the challenges are as staggering as the potential. cooling isn't the only hurdle. Maintaining that cold while scaling up qubit counts is like trying to ice skate uphill. Current systems might house dozens or even hundreds of qubits, but practical applications demand millions, all operating in perfect sync. Some researchers are exploring topological qubits, which could resist errors through their inherent structure rather than brute force cooling. Others are investigating hybrid systems that combine classical and quantum computing, offloading simpler tasks to conventional processors to ease the burden on their ultra-cold counterparts. The future of cold doesn't stop at quantum computing. The same cryogenic breakthroughs could revolutionize other fields, from astronomy, where supercooled sensors detect faint cosmic whispers, to medicine, where frozen preservation might one day pause biological time for long-distance space travel. Cold isn't just a tool, it's a gateway to realities we've barely begun to explore, where the rules of physics bend and the impossible becomes routine. And as we inch closer to harnessing that potential, one truth becomes clear. The coldest places in the universe aren't just curiosities, they're the birthplaces of tomorrow. The power to manipulate temperature isn't just a scientific breakthrough, it's an ethical crossroads. As we learn to harness extreme cold from the cosmos, we're faced with a pressing question. Just because we can cool our planet, does that mean we should? Proposals like stratospheric aerosol injection, which would mimic volcanic eruptions by spraying reflective particles into the upper atmosphere to bounce sunlight back into space, sound like elegant fixes for global warming. After all, nature already does this. When Mount Pinatubo erupted in 1991. It cooled the Earth by half a degree Celsius for nearly 2 years. But borrowing the universe's chill to combat climate change isn't as simple as flipping a thermostat. The side effects could ripple through ecosystems in ways we can't yet predict. Take the Arctic as a cautionary tale. Artificial cooling might slow ice melt, but it could also disrupt jet streams, shifting rainfall patterns that millions depend on for agriculture. Or consider ocean currents. Tampering with global temperatures might inadvertently stall circulations like the Gulf Stream, which keeps Europe temperate. These systems are finely balanced like a house of cards. Tweaking one piece could collapse entire networks of climate stability. And then there's the political dilemma. Who gets to decide how cold is cold enough? A decision made by one nation to cool the planet could trigger droughts or famines in another, sparking conflicts over who controls the thermostat of Earth itself. Yet the allure is undeniable. If we could precisely dial down temperatures, we might buy time to transition away from fossil fuels or protect vulnerable species from overheating. Some experiments are already creeping forward. Startups like Make Sunsets have launched small-scale balloon tests to release reflective particles, despite outcries from scientists warning of premature deployment. It's a modern-day gold rush, with investors and governments racing to claim stakes in climate intervention before the rules are even written. The irony is stark. In our quest to mimic the cold of space, we risk repeating the same mistakes that got us here, acting first and understanding later. The universe's coldest places evolved over billions of years, their extremes shaped by natural forces. Our interventions, by contrast, would be swift and irreversible. Once aerosols are in the stratosphere, there's no undo button, only decades of unintended consequences. Perhaps the answer lies not in grand geoengineering schemes, but in humility. Instead of trying to control Earth's climate like a machine, we might learn from the cosmic balance that keeps the Boomerang Nebula frigid or neutron stars precisely chilled. Nature's coldest realms aren't brute force experiments, they're the result of delicate equilibriums honed by time. If we're to borrow the universe's wisdom, our first step shouldn't be spraying the skies. It should be listening. Life in the universe doesn't always play by Earth's rules, especially when it comes to cold. Right here on our own planet, organisms called extremophiles laugh in the face of freezing temperatures, thriving in places like Antarctica's blood-red brine lakes or Siberia's permafrost, where they've been frozen for millennia only to wake up when thawed. These microscopic survivors hint at something extraordinary. If life can cling to existence in Earth's icy extremes, why not on the frozen moons of Jupiter or Saturn, where oceans slosh beneath miles of ice? Take Europa, Jupiter's enigmatic moon. Beneath its cracked, frozen shell lies a global ocean kept liquid by tidal forces, a dark, salty abyss where hydrothermal vents might churn out heat and nutrients, just like they do in Earth's deepest seas. On our planet, entire ecosystems thrive around these vents, fueled not by sunlight but by chemistry. Now imagine that same scenario playing out in Europa's pitch-black depths, where organisms could exploit chemical reactions we've barely begun to understand. The cold here isn't a barrier, it's a preservative, a stabilizer that might slow life's pace to a crawl while giving it billions of years to adapt and evolve. Enceladus, Saturn's icy geyser moon, offers another tantalizing possibility. Its south pole spews towering plumes of water vapor laced with organic molecules, like a cosmic soda can shaken and opened. These jets hint at a subsurface ocean where chemistry is active, not frozen solid. For life, this could be a delivery system. Compounds formed in the moon's warm interior get launched into space, freezing into tiny ice grains that might seed other worlds or even preserve biological material in suspended animation. The cold of space acts like a pause button, stopping the clock on delicate molecules until they find a new home. But what would life look like in these frigid realms? It might not resemble anything we recognize. On Earth, cold slows metabolism. Some Arctic microbes divide just once every 100 years. On Europa or Enceladus, life could operate in ultra-slow motion, with biochemical processes stretched over centuries or millennia. Instead of relying on fast-paced reactions like ours, alien organisms might use cold, stable enzymes or antifreeze proteins to keep their cellular machinery from locking up. Some scientists speculate they could even exploit quantum tunneling, where particles phase through barriers at low temperatures, enabling chemistry impossible in warmer environments. The real game changer is time. Cold doesn't just preserve life, it might extend its lifespan indefinitely. Imagine a microbe trapped in ice for 1 billion years, its metabolism so sluggish it's practically immortal. If such organisms exist on icy moons or drifting between stars, they could be the universe's ultimate survivors, outlasting stars and civilizations. This raises a spine-tingling question. Could the coldest corners of space be teeming with ancient, slow-motion life, waiting for the right conditions to awaken? The search for answers is already underway. Missions like NASA Europa Clipper and ESA's JUICE will scan these frozen worlds for chemical signatures, unusual ratios of hydrogen or methane that betray biological activity. Meanwhile, labs on Earth simulate alien oceans, testing how life might function at sub-zero temperatures. Each experiment is a step toward rewriting the definition of habitable, proving that life isn't just a fluke of warm, sunlit planets. It could be a silent, patient force, thriving where the universe is at its coldest and most mysterious. The race to conquer extreme cold isn't just about scientific curiosity. It's a high-stakes battle for global supremacy, where nations and corporations scramble to control the technologies that could redefine the next century. Picture this: quantum computers, unhackable encryption, and propulsion systems that could take us to Mars in weeks instead of months, all hinging on mastering temperatures colder than deep space. The US and China are pouring billions into ultra-cold research. treating it as the new space race, while private giants like SpaceX and Blue Origin eye cryogenic breakthroughs to fuel interplanetary ambitions. This isn't just about bragging rights, it's about who sets the rules for the future. At the heart of this Cold War lies quantum technology. China's MISHA satellite, which uses quantum encryption to send unhackable messages, relies on supercooled components to maintain quantum coherence. Meanwhile, the US National Quantum Initiative is racing to develop even colder, more stable qubits, with DARPA funding labs that push temperatures to within a billionth of a degree above absolute zero. The military implications are staggering. Imagine satellites that can't be eavesdropped on, or sensors so precise they detect stealth submarines from orbit. The nation that cracks ultra-cold quantum networking won't just lead in computing, it could dominate global security. But the competition isn't limited to governments. Private companies are betting big on cryogenics as the key to space dominance. SpaceX's Starship uses supercooled methane and oxygen to maximize fuel density, enabling longer, faster voyages. Blue Origin's lunar lander plans hinge on cryopreserved hydrogen, a volatile fuel that demands temperatures near -250 degrees Celsius to remain stable. Even startups like Quantum Machines are entering the fray, selling ultra-cold refrigerators to labs worldwide, turning niche science into a lucrative industry. The message is clear: cold isn't just a scientific challenge, it's a trillion-dollar market. The stakes go beyond Earth. On the Moon's shadowed craters, where temperatures dip below -250 degrees, water ice could power future colonies and rocket-fuel depots. China's Chang missions and NASA Artemis program are already scouting these frozen reserves, knowing that whoever harnesses them could control the first off-world supply chain. It's a modern-day gold rush, except the treasure isn't glittering ore, it's the ability to survive and thrive in the universe's harshest environments. Yet for all the promise, the Cold War has a darker edge. The same cryogenic tech that could revolutionize medicine by preserving organs for transplant might also be weaponized, enabling long-term storage of biological agents or even suspended animation for soldiers. And as nations hoard patents on ultra-cooled materials, the risk of a fragmented scientific landscape grows, where breakthroughs are locked behind national borders instead of shared for collective progress. The irony is profound. The coldest places in the universe, once thought barren and inert, have become the hottest battlegrounds for human ambition. Whether this race leads to collaboration or conflict, one thing is certain: mastering cold won't just change technology. It will redefine power itself. Even in the deepest freeze, nothing in the universe is truly dark. Every object, no matter how cold, emits a faint whisper of light, a phenomenon called Blackbody radiation. Picture an iceberg drifting in space. To our eyes, it's invisible against the black void, but point an infrared telescope its way, and suddenly it glows with a ghostly warmth. This isn't magic, it's physics. The colder an object is, the longer the wavelength of light it emits, shifting from visible red to infrared and beyond. At near absolute zero, this glow becomes vanishingly faint, but it never fully disappears. That's why telescopes like the James Webb can detect frigid gas clouds light years away. They're not seeing reflected starlight, but the object's own subtle thermal signatures. The brilliance of blackbody radiation lies in its predictability. Heat a piece of iron, and it progresses from dull red to yellow-white as its temperature rises. That color shift follows a precise mathematical relationship, allowing astronomers to reverse engineer the temperature of cosmic objects just by analyzing their glow. A cloud of interstellar hydrogen at 20 Kelvin emits a very different spectrum than a protostar at 3000 Kelvin, and those fingerprints reveal everything from chemical composition to density. It's how we know the Boomerang Nebula is colder than the cosmic microwave background. Its Blackbody curve peaks in the millimeter range, betraying its record-breaking chill. But here's the twist: Blackbody radiation isn't just a passive glow, it's a time machine. When we observe the cosmic microwave background, we're essentially measuring the Blackbody radiation of the early universe, cooled over 13 billion years to a mere 2.7 Kelvin. The near-perfect uniformity of that glow tells us the cosmos was once a searing plasma, while its tiny fluctuations, variations of just 1 part in 100,000, encode the seeds of galaxies and superclusters. Without Blackbody radiation, we'd be blind to these whispers from the dawn of time. Modern astronomy leans on this principle to uncover hidden cosmic layers. ALMA, the radio telescope array in Chile, tunes into millimeter wavelengths to map cold dust in planet-forming disks, while the upcoming SPHEREX mission will scan the entire sky in infrared, cataloging Blackbody emissions from millions of asteroids, comets, and distant galaxies. Even the search for extraterrestrial life benefits. If a rogue planet drifts between stars, its faint Blackbody glow might betray oceans beneath an icy crust. What makes this phenomenon so transformative is its universality. From the coldest nebula to the warmest star, everything emits light according to its temperature. That means there are no true shadows in the cosmos, only wavelengths we haven't yet learned to see. And as our telescopes grow more sensitive, the universe's coldest corners are finally stepping into the light. Hollywood loves showing astronauts freezing solid the moment they're exposed to space, but reality plays by different rules. The truth about cosmic cold contradicts almost everything pop culture has taught us. Space isn't cold like your freezer. It's the absence of nearly everything, including the air molecules that make cold feel familiar. If you found yourself floating unprotected in the void, you wouldn't turn into an ice statue. You'd actually overheat first as your body struggled to shed warmth without air or liquid to carry it away. Your sweat would boil off your skin before the slow process of radiative cooling even began. This misconception stems from how heat behaves in a vacuum. On Earth, cold feels immediate because air molecules constantly collide with us, stealing body heat through conduction. But space is emptier than any lab vacuum. A single cubic meter might contain just a few stray atoms. Without particles to carry heat away, the only cooling method is radiation. Your body slowly leaking infrared waves into the abyss. That process takes hours, not seconds. Meanwhile, unfiltered sunlight would roast you at over 120 degrees Celsius on your sun-facing side, while your shadowed side might eventually drop to minus 160. The real danger isn't freezing its temperature extremes with no atmosphere to balance them. Even more surprising, some spacecraft struggle more with overheating than freezing. The International Space Station spends half its orbit baking in sunlight, requiring elaborate radiators to dump excess heat. Meanwhile, the James Webb Space Telescope's sun shield isn't just for blocking light. It creates a temperature difference of over 300 degrees between its scorching, hot side and the cryogenically chilled instruments facing deep space. These engineering challenges reveal the true nature of cosmic cold, not as an active force, but as the baseline state of a universe where heat is the exception rather than the rule. The coldest natural places in space achieve their record-breaking temperatures through expansion, not just absence. When gas from a dying star rushes outward at supersonic speeds, like in the Boomerang Nebula, it's like the universe's version of spraying compressed air and feeling that can get colder. This adiabatic cooling happens because the gas does work as it expands, converting thermal energy into motion until particles barely jiggle at all. On Earth, we mimic this in refrigeration cycles, but space does it effortlessly on cosmic scales. These realities reshape how we explore. Mars rovers, for instance, don't carry traditional heaters. They use radioactive decay units that produce warmth for decades because battling radiative heat loss is easier than fighting conductive freezing. Future lunar bases might bury habitats in permanently shadowed craters, not just for cold, but for stable temperatures away from the sun's wild swings. Understanding cosmic cold isn't about debunking myths, it's about seeing the universe as it truly operates, where the rules defy both intuition and Hollywood logic. Every accurate detail brings us closer to surviving and thriving in the final frontier.